So, trying to move forward from AI application to the AGI application, the key is that networks should have the ability to generalize. Even if they only learn the basics, they should be able to pull out more information from that. And as part of that, the training distribution shouldn't be the same as the test distribution. For example, if you learn giraffe and zebra, well, if you go to the zoo and see them both together, that's outside of the distribution if you learn them all in a single shot. And you also want to avoid combinatorial explosions. This will allow complex networks. So I'd like to focus on networks that show these properties. And one of these networks is based on massive feedback to the inputs. So in the brain, you have feedback at every level. There is feedback back and forth. And in this model, there's no emphasis on weight parameters. Instead, it's input feedback. That means feedback from the outputs back to the inputs. And that happens during testing, not during training. And so how does this sort of approach avoid combinatorial explosion? If you have inputs going to an output, there aren't connections to other outputs because the bigger the networks get, the more you have to work on that, or inputs that aren't associated or inhibitory connections. There's only connections between inputs and outputs. That's it. This whole network is built on connections between inputs and outputs, no lateral connections at all. And instead, it's iterative and bidirectional. So if an output gets two inputs, that output has to project back to the inputs, and the same thing with another representation has to project back. And there's this feed forward, then feed back, then feed forward, then feed back, and that's how the system works. And I'll give you a small example. So white is active, black is inactive. Let's say both my inputs are active, and assume initially both the outputs are active. Well, at the next stage, but if you see, this actually fits best to the cell that captures both inputs. So after the first iterative phase, inhibition, one of the inputs gets 2 units of inhibition while the other doesn't, which in turn, then in the feedback phase, affects the output that only uses that input. And that continues, and that separates things out more and more. And then eventually, you get a separation of, well, this representation is best for that input. And that's how basically this network works. And it shows it resolves patterns. So if input A is active, node 1 will be classified as A and B, then it'd be node 2. It also can take half, or it's not binary inputs that you have to put in. If you put in half, it'll output half. And it tries to categorize best all of the information based on the representation it has. So, for example, if the setup is like this, well, cell 2 is only getting half of its inputs, you get a half of activation. A and B, well, then cell 2 is matched. But if you get A, B, and C, well, there's a conflict here, because B can be represented by either 2 or 3, and they compete with each other because it's not a complete match. So neither of the cells get complete activation, and the same thing goes if only B is activated, then even less. But if there's a match, of course, you get a complete match. And this sort of network does interesting logical analysis based on the system of representations. So now if I set it up like this, if you get the same matching again and the same matching, but now if I have all 3 there, the network wants to represent everything with the priors that it learned, but with the least amount of mutual overlap. And so the representations will intercommunicate with each other and come up with, well, cell 1 and cell 3 best capture all of the inputs at once without any ambiguity. And so given this sort of situation, you get 1 and 3. And in this way, this feedback system is performing logic as well. And of course, it works with the other configurations, with the other inputs as well. And this can be changed as well. So if I have at infinitum kind of these things connected, it's going to matter if node 1 exists or node 1 doesn't exist for the representation. And so this has general properties. This is data that's not in the paper, that's just brand new, to show more of this sort of generalizability that I'm talking about. So if I set up a network, I teach it single letters, and then I give it multiple letters. I've never trained it on multiple letters, but I give it multiple letters at once. And so I use a feature extractor, which is general computer vision. And so let's say each feature comes up as an input, and those inputs go to the network. And when I compare data between neural networks, SVMs, k-nearest neighbors, one nearest neighbor, and this input feedback, so if I present 2 letters at once, input feedback tends to do the best, but others do okay. But when I do more, like 4, input feedback is the only method that's able to classify those 4 letters as being the ones that are present in the scenes. The other methods fall apart because they're trained with the assumption that their test distribution is going to be the same as the training distribution. So why isn't this everywhere and everybody using this? Well, this uses feedback, and feedback is nonlinear. So it's really hard to prove, besides specific examples, mathematical properties about this. So, but on the other hand, this is really important for the development of AGI, because it's able to generalize outside its training distribution and avoids combinatorial explosion because of its connectivity. So I think this is a great forum to discuss methods like this, which may be harder to analyze mathematically and to say exactly, well, you want to use this exactly here, but it gives the flexibility that's needed. And I don't know how my time is, but I timed everything to be short, so.